All right, so welcome to the review lectures for the Calculus 3 course. There are 4 review lectures. The first 2, Review 1A and 1B, basically will take everything up to the end of integration. And reviews 2A and 2B will deal with reading assignments 4 and reading assignments 5. This cover slide basically just shows the contents for review lecture 1A. I'm not going to go into the detail on this slide. And also, as I go through each one of these topics, I'm just going to be quite general about it since most of the details are in the previous lecture slides. So this is more or less just to give you a general overview. All right, so we first started with sketching surfaces. And so traces and level curves and cylinders were sort of concepts that we basically utilized to help us visualize, what the actual surface looked like. And so I basically put in table form trace, level curves, and cylinders. And so for a trace, let's take a particular example here where you're given y equals x squared 6 plus z squared over 16. What this just meant was that you held one of these values at a constant, typically 0, and then graphed x as a function of z, or you held x at 0 and graphed y as a function of z. And so this is just an example illustration showing that if you hold one of these fixed, then effectively what you are drawing is just a line, and that line basically would be, in this case, it's a closed contour. If it were a plane, then it'd be a single line. For level curves, basically, we took a function, for example, this one, and we take the value of z, and we held it constant, and we take a number of values of z and hold them constant, and then we plot y as a function of x for different values of z, and so we project what happens in the z direction in terms of a series of contours representing different values of z. In the case of cylinder, this occurred when, for instance, you had an equation where it was apparent that one of the variables was not specified, which meant that effectively that variable could take on any value of the real number set. So for example, x squared plus 4y squared equals 16. Z could be anything. So this would be more or less an ellipse that's been extruded in the z direction. Next thing we did was to look at limits in the multivariable case, but restricted ourselves to more or less 2 variables. And there were only 2 issues that came up. One was, how do you go about proving a limit exists or it does not exist? And so there were basically a few techniques that we basically explored. If you want to prove the limit exists, then try to prove this assertion using specific techniques such as factorization, algebraic conjugate, substitution of new variables, and basic theorems for analytical functions. So that was basically our toolbox. On the other hand, to prove the limit does not exist, also called the two-path test, it uses a contrapositive approach so that you can find at least 2 paths for which the limit is different than the limit does not exist. And typically in this case, you use the substitution of variable technique for the two-path test. All right, so definition of continuity, again, this is just going to be very brief. You'll basically have to show that all of the 3 conditions are satisfied. So that means that if, for instance, condition 1 is satisfied and condition 2 is not satisfied, there's no need to move on to proving that condition 3 is satisfied. So all must be satisfied. We also looked at continuity of composite functions. And so basically we looked at the function g and the function of x to prove continuity for both, and then more or less we were able to show that the function as a whole was continuous. All right, so then we looked at partial derivatives, and this was a new material, so we defined what we meant by partial derivative. We are dealing only with 2 variables, so we can take a function and take its derivative with respect to x, which would be f partial x, and then do the same thing for f partial y. And this is a standard definition that you used in Calculus 1 when you talk about derivatives. But in this case, you would be holding one of the parameters fixed, and the other one would be varied. So Next thing that we looked at was the equality of mixed partial derivatives. So in this case, basically, if you, for instance, were to take the derivative with respect to y followed by x, or the other way around, then the question is that what is the relationship between the two? Well, if fxy and fyx are continuous, then fxy is equal to fyx. And you could extend this basically if you're taking triple differentiation. So for example, in the statement below, fxyx equals fxxy equals fyxx, all partial derivatives basically would have to be continuous, in which case all those three combinations shown there would be equivalent. All right, and then the question came down to what we meant by differentiability. We're dealing with multivariable calculus. And so here basically you have the theorem 15.5 for conditions for differentiability. And then you could also apply the contrapositive argument, which in some cases was much easier to work with. So that's why both are indicated. And then another useful theorem, theorem 15.6, was that if it's differentiable, it implies continuity. And then a contrapositive argument basically could also become useful as well. Again, it depends on the nature of the problem that you're trying to solve. Okay, so the next thing we did was to look at the chain rule. And the chain rule essentially would say, if I'm given a function which is a function of other variables, and I'm interested in understanding the relationship between the differential and some other quantity. So for example, here it's given that this productivity is a function of L, K, and R, but L is a function of U, K is a function of I, and R is a function of T. And I'm interested in what is the relationship between productivity and unemployment rate. Then the chain rule said that I basically have to take dP with respect to L followed by dL by du. And here, for instance, are the other cases. If I'm interested in how productivity is influenced by interest rates, it would be this expression, and by time, this expression. I can also look at this diagram, or look at these expressions in terms of a diagram. So this looks like a series of chain links. That's why it's called the chain rule. At the top is P. The next layer is LKR, and the next layer is UIT. So for this example, there's just straight linkages to one variable. Partial derivatives is where we use the squiggly d value. This basically exists whenever you have bifurcation point. In other words, this basically branches. So all these branches will be partial derivatives. On the other hand, when we go from here to here, it's direct. There's no other potential path, so this becomes a direct derivative. Similarly, when we talk about P with respect to U, this is a straight path. There's no branching taking place. It just goes straight down. So this is a direct derivative. So we have a direct derivative here, a direct derivative here, and a partial derivative here. And we looked at a number of other cases where this was the situation as well. And can get more complicated because it could be a function of two variables, various situations we looked at. In particular, we found that we could use the chain rule for differentiation, in particular if you're dealing with an implicit function. So for instance, if you have z as a function of x as a function of y of x, but you're not necessarily given it y of x, but nevertheless, if you were able to put y in terms of x, then this expression is perfectly valid. All right, and then we're going to assume that z is a level curve, which means z equals constant. So if we apply the chain rule to this expression, then we'd have dz dx, which is a direct derivative, is df dx, which is a partial derivative, df dy dx, and the equivalent diagram is shown over on this side. But since z is a constant, it's a level curve, that means this is equal to 0. From this, therefore, we're able to basically compute dy dx. If this were an implicit form, you would not be able to extract y of x, and therefore you would not be able to compute dyx. So this approach allows us to compute dy dx given an implicit function. We can extend this basically to more than two variables. So for instance, if we have x, y, and z, but z is a function of x and y, then w now becomes a level surface. If we apply the chain rule, we can obtain the value for dz dx and dz dy. So if we do w dx and break this out, this is df partial x plus dfz dz dx. And again, because it's a level surface, w is a constant, so the derivative of this will be equal to 0. So you can solve for dz dx partial. Similarly, you can do it for dy dy partial. And again, because it's a level surface, the derivative is equal to 0. And the diagram here basically would be representing these computations that I've shown here. All right, so then the next thing we did was the directional derivative and gradient definition. Why directional derivative? Because depending on which direction you go, you see a different slope. And so a directional derivative basically it just says the actual physical slope if you're moving in a particular direction, right? And so that's why I mentioned here the slope of the curve at a given point in the direction of the curve traversal, all right? So you're basically charting a path down some surface, but if you project that path onto the xy plane, that's the direction of the traversal that we're referring to. And so we went through in quite detail. These are the expressions that we had. I'm not going to go into further detail since I don't have any diagrams at this point. And so we had two different ways of looking at the problem. One is the parametrized representation of the contour, or the direction in which we're traveling, and an explicit representation. In the parametrized representation, we basically would represent x and y in terms of parameterization variable t, but in the explicit representation, we would represent y in terms of x. And so effectively, we end up with slightly different expressions, but if you go through to the end, you find effectively you get the same expressions, no matter which approach you take. Now this term here, we called the gradient, and we basically defined it as such, and f partial x, f partial y. And so if we write now the directional derivative, it's nothing more than the dot product or the projection of the gradient vector in the direction in which you are traveling. That is the projection on the xy plane. And so this could be represented as grad f, and this is a unit vector, u. This can also be written in terms of the magnitude of the gradient, the magnitude of u, which is 1 cosine phi, and then depending on what the angle is between the direction you're going and the direction of the gradient vector, which is the direction in which the slope is a maximum, right? We were able to look at different scenarios. So if it's perpendicular, which is cosine 0, which means you're walking around the hill, which means the slope is equal to 0. And so this is something we covered in great detail in an earlier lecture. Then we basically looked at tangent planes, but we extended this notion to other applications, in which case we were dealing with physical problems. And we didn't necessarily call them tangent planes, but mathematically that's what they were. And so we looked at a multivariable Taylor series expansion of a particular function. And so we looked at this as being one approach for tangent planes, and also defining the equation of an arbitrary vector that is orthogonal to the gradient at a point on the surface. So two different approaches we used to determine a tangential plane. For the multivariable Taylor series expansion method, we took the function, right, which is in this case two variables, and we expanded outwards. This is in matrix form. So C would be evaluated at the point AB. This would be the gradient vector dot D, where D was just the difference vector between x and the established values at a given point, y and y minus b. That's the gradient vector. This would be evaluated at the position of interest. And then we left with the second order term, which we wrote in this form. This is D, again, this vector. So this would be in row form, and this would be in column form. And this was a matrix, which we called the Hessian matrix. We didn't make use of this, but if you were looking at, for instance, determining min and max for basically a two-variable function, then you would end up basically investigating the properties of this Hessian matrix. Of course, we did not have time to do that in this course because we have something called a reading week now. All right, the vectors, the gradient f is basically basically what we're calculating. The d of transpose, which you're basically taking this row vector and making it to a column vector, would look like this. The other approach was to find the equation of the tangent plane at a point on the surface, and so this basically would matter of just considering position x, y, z. at any point on the tangent plane and create the vector between this point and the point ABC on the surface defined by fxyz equals 0. This is basically just written here in implicit form. Then the gradient vector dot x minus a, y minus b, z minus c. So this is an arbitrary vector, basically which has its tail positioned at the point of interest on the surface. This is perpendicular to the surface at the given point, x equals a, y equals b, and z equals c. If you want a tangential plane, then this vector and the vector perpendicular to the surface must be 90 degrees with respect to each other, in other words, orthogonal. So that means this dot product must be equal to 0. Under these conditions, basically, when you solve this equation, you get an equation that will be linear in x, y, and z, which is by definition going to be the tangential plane. So this is basically the two approaches that we took when we dealt with tangent planes. All right, we then looked at a sensitivity analysis, and so here what we were interested in knowing is that if you're at a given point and you perturb it slightly in any given direction, direction x and direction y, how does the value z change? And so this would be a differential. So z minus c would be the change on z. How is affected by changes in x and changes in y, which meant that all we need to do is compute the partial derivative with respect to x, evaluated at x equals a, y equals b, and partial with respect to y evaluated x equals a and y equals b. And so we went through this process, and so effectively we could do calculations which we call sensitivity analysis. We also find that quite often it's simpler to write these equations in per unit form so that basically we compress the number range that we're working with. And so per unit analysis would require us to divide through by z throughout, but also everything in this system would have to be in per unit form. So delta x can be converted to per unit by dividing by x and then multiplying through by x. Here we would divide through by y and multiply through y. So here, for instance, the z is common to all, but here we have an x here and an x here. This is going to be per unit. This is per unit, right? And so if we take this now and carry through, right, then we will find that we end up with a simplified values. These end up becoming constants that have been calculated, right? And these will be also constant that would be calculated. And so what we end up with then is an expression between per unit z is some constant time per unit x plus some constant time per unit y. And so this sometimes is simpler to use rather than have to work with basically the raw numbers. So the last thing we looked at was basically using, looked at dynamic systems using, again, multivariable Taylor series expansion. We called this small signal analysis. So we had state space equations. In this case, there are only two variables concerned. And so this basically is a state space equation which is nonlinear because the equation on the right involves a state variable which is of a nonlinear form, which means in this case x1 squared. The output equations also, in this case the output equation y2 is nonlinear. Why? Because it depends on the fourth power of one of the input variables. So in this case, the output variable depends on the state variables, x1, x2, as well as some arbitrary input variables, u1 and u2. All right, so then we could also write the state variable equilibrium condition in matrix form. And equilibrium was basically when there's no change taking place in the state variable, which means dx1 dt equals 0 and dx2 t equals 0. So that means these two would be 0. And you're left with basically trying to compute the equilibrium values. U1, U2 would be the input equilibrium values. And what you're computing is what is x1 equilibrium, x2 equilibrium. We basically use x subscript 1, 0 and x subscript 2, 0 to represent the equilibrium values of x1 and x2 respectively. So in this case, you would have two equations and two unknowns. x1 naught and x2 naught are unknown. And you solve. This could in fact be a nonlinear equation that has to be solved. And then the final form of the small signal model, which was obtained by basically expanding out the Taylor expansion to first order That means you only retain expressions involving first-order partial differential equations. We end up basically that the small signal perturbation, which we refer to x1 hat for this state variable, x2 hat for the other state variable, was related to some matrix times the small perturbations in x1 hat 2 plus another matrix and perturbations in the input variables u1 and u2. This involved matrix involving partial derivatives, and we call them Jacobian matrices. One involving the state variables and one involving the input variables. So for the output equilibrium point, once we had solved for the equilibrium points for x1, x2 naught, and we know u1, u2 as equilibrium points, then we end up with two equations, right? Substitute in, and this gives us the equilibrium output value for y10 and the equilibrium output value for y20. On the other hand, if you want to look at the small signal perturbations, then y hat 1 hat and y2 hat would be the small signal perturbations in the output signal, and they were related to perturbations in the state variables and perturbations in the input variables. In this case, we'd end up again with matrices here and matrices here involving partial derivatives. And so again, we call these Jacobian matrices. Anything involving a matrix with a partial derivative in this is called a Jacobian matrix. And these matrices are always related to the first order terms in the multivariable Taylor series expansion. You could also convert these equations to per unit form, right, which we basically did show. However, this is not something that you're responsible for. But in future, you might find it interesting, so you can refer to the slides where we basically looked at a number of examples involving single differential equations and also two coupled differential equations. Okay, so that basically concludes Review 1A lecture. Thank you for listening.